Hi, everybody. It's Professor Mitchell. Today we're talking about Chapter 7, which is the central limit theorem. And that corresponds with one assignment in the Newton-Alta homework. That assignment is called the central limit theorem. So we're going to be talking about two different forms of the central limit theorem, the central limit theorem for means and the central limit theorem for sums. They're actually pretty similar. All right, so the idea behind the central limit theorem is that you have an original distribution of data, and then if you collect samples from that distribution, let's say samples of size 10, and you find the mean for each sample, we're looking at what does the distribution of those means look like, and also what does its standard deviation look like. Okay. All right, so one thing to know about this sampling distribution is that as long as the samples are large enough, and by large enough we usually mean at least 30, that distribution is going to be normal. It doesn't matter if the original distribution is normal. Okay? If the original distribution is normal, then the samples don't have to be size 30. They could be smaller. All right, but by making the samples at least size 30, it guarantees that this sampling distribution will be normal. All right, so first we talk about the central limit theorem for means. This theorem says that if you keep drawing larger and larger samples, and the example that you go to 5 or 10 dice, and you calculate the mean of the numbers that come up on those dice, then those sample means will follow a normal distribution. That normal distribution of the sampling distribution will have the same mean as the original distribution. Its standard deviation, though, will be smaller. So if the standard deviation of the original distribution is sigma, then the standard deviation of the sampling distribution will be sigma divided by the square root of n. So the larger your samples are, the smaller that standard deviation is. Okay, so suppose x is a random variable with some distribution that may be known or unknown. It may or may not be normal, for example. This is the original distribution. So the notation that we're using here is mu sub x stands for the mean of this original distribution. Sigma sub x stands for the standard deviation. Okay. So now if you take the sampling distribution of the mean, which is called x bar, this capital X bar, that consists of sample means, of samples of size n. So what happens there is that the random variable x bar, which consists of sample means, tends to be normally distributed. So this notation, which I think you've seen something like this before, this says that x bar follows a normal distribution with a mean of mu sub x, that's the mean of the original distribution, and a standard deviation of sigma sub x divided by the square root of n. So you take the original standard deviation and divide it by the square root of n. All right, so here's an example. An unknown distribution is created by the test scores of a nationwide standardized test. This distribution has a mean of 90 and a standard deviation of 15. A sample with size n equals 35 was randomly drawn from a population. Using the central limit theorem for means, what is the mean and the standard deviation for this sample mean distribution? Okay, so that's exactly the kind of thing we're talking about right now. The central limit theorem for means says that the mean of the normal distribution of sample means is equal to the mean of the original distribution. So the mean that they're asking about, the mean of the sample mean distribution, will also be 90. central limit theorem also says that the standard deviation of this new sampling distribution is sigma divided by the square root of n. So if our samples are size 35, then the standard deviation of our sampling distribution is going to be sigma divided by the square root of n, which is 15 divided by the square root of 35. That comes out to about 2.535. All right, here's another example. This would be a good one for you to try. It's very, very similar to the last one. So if you're feeling confident and you want to try this one, then pause the video and go ahead and try this. An unknown distribution is created by the birth weight of males in a certain country. This distribution has a mean of 7.8 pounds and a standard deviation of 1.2 pounds. A sample with size 150 was randomly drawn from the population. Using the central limit theorem for means, what is the mean and the standard deviation for this sample mean distribution? Okay. So again, the mean of the sampling distribution is the same as the original distribution. It's still 7.8, but the standard deviation becomes smaller. Instead of 1.2 pounds, it's going to be 1.2 pounds divided by the square root of 150, and that comes out to approximately 0.098. All right, here's another example. Again, pause the video if you'd like to try this one first. An unknown distribution is created by the average number of grams of gold per million tons of seawater. This distribution has a mean of 1 gram and a standard deviation of 2 grams. A sample with size n equals 200 million tons was randomly drawn from the population. Using the central limit theorem for means, what is the mean and the standard deviation of this sample mean distribution? So again, the mean of the sampling distribution is the same, it's still 1, but now the standard deviation, instead of being 2, it's going to be 2 divided by the square root of 200, which comes out to about 0.141 grams per million. Okay, so here is a slightly different form of the central limit theorem, called the central limit theorem for sums. This theorem says that if you keep drawing larger and larger samples and continue to take their sums instead of taking their means, the sums will also form a normal distribution. Suppose X is a random variable with some distribution that may be known or unknown, normal or not normal. This is the original distribution. So again, we'll call the mean and the standard deviation of that distribution mu sub x and sigma sub x. So this new distribution consisting of the sums of the samples, we'll call that sigma x, the sum of the x's. Okay, so what this says is that this new random variable, the sum of the x's, follows a normal distribution with a mean. Hang on, I'm going to get my pen here. I'm not super crazy about how they wrote this. With a mean of n times the original mu sub x and a standard deviation of square root of n times the original sigma sub x. So you multiply the original mean by n, you multiply the original standard deviation by the square root of n. Okay. As stated in the notation, there are two important parameters to this formed normal distribution. Those are the mean, which again is, oh, hang on a second, lost track of my mouse. There we go. All right. This is the only way for me to find my mouse when I lose track of it. I kind of have to leave a trail of breadcrumbs. All right, so the mean of the of sigma x, the sum of the x's, is n times the original mean. The standard deviation is square root of n times the original standard deviation. Okay, so here's an example. An unknown distribution is created by the test scores of a nationwide standardized test. This distribution has a mean of 138 points and a standard deviation of 45. Samples with size 50 were randomly drawn from a population. Using the central limit theorem for sums, what is the mean and the standard deviation for the distribution created by sums? All right, so since the mean of the original distribution is 138 and the samples are size 50, that means that the mean of the sums is going to be 50 times 138, which comes out to 6,900. And the standard deviation is going to be the original sigma, which is 45, times the square root of n. So that's going to be 45 times the square root of 50, which is about 318.2. Okay, here's another example. You could try this one. An unknown distribution is created by the birth weight of males in a certain country. This is just like one we had before. The distribution has a mean of 7.8 pounds and a standard deviation of 1.2 pounds. A sample with size 150 was randomly drawn from the population. Using the central limit theorem for sums, what is the mean and standard deviation for the sample? I think that's a typo there. I don't think that should say sample mean distribution. That should say the sample sum distribution. That was probably just a copy and paste. Okay, sorry about that. All right, so again, the mean of the sums is n times the original mean, so that's going to be 150 times 7.2, which is 1,080. And the standard deviation is going to be sigma times the square root of n. 1.2 times the square root of 150 is about 14.7. Okay. Here's another one, and again, they put the word mean. I really don't think they meant to put that there. Let's get rid of that. Okay, but it does say using the central limit theorem for sums. So I'm sure this is what they want me to do. All right, an unknown distribution is created by the average number of grams of gold per million tons of seawater. This sounds familiar. This distribution has a mean of 1 gram and a standard deviation of 2 grams. A sample with size 200 million tons was randomly drawn using the central limit theorem for sums. What is the mean and the standard deviation of this sampling distribution of sums? All right, so again, for the new mean, you do n times the original mean. 200 times 1 is 200. And the new standard deviation is going to be sigma times the square root of n, which is 2 times the square root of 200. That's about 28.28. Okay, now we're going to get into some problems where we calculate some probabilities. So this is going to be similar to what we did in chapter 6. If you remember, we would, they would ask us a probability question about a normal distribution. We would change the values in the problem to z-scores using this formula. Okay, so we're going to be doing something similar now, except we just have to make sure that we're using the correct mean and the correct standard deviation. Okay, so if we're using central limit theorem for means, we just have to remember that the mean of that sampling distribution is the same as the original distribution. However, the standard deviation is now sigma divided by the square root of n. Okay, so when you go to calculate your z-score, instead of, well, this looks like the formula from chapter 6, except for the x bar, okay? It follows the same format though. Value from the distribution. This is the mean of the distribution. This is the standard deviation. So this is how you're going to calculate your z-score when you're using central limit theorem for means. So let's see. Okay. And then to use central limit theorem for sums, it's the same idea. The mean of that distribution is n times mu. The standard deviation of that distribution is sigma times the square root of n. Okay, so here's an example. An unknown population distribution has a mean of 90 and a standard deviation of 15. A sample of size 31 is drawn randomly from the population. What is the probability that the sample mean is between 85 and 92? So there's only one thing that I might have done differently in this problem. Let me just peek ahead here. Yeah, I thought I noticed earlier that they didn't have this. In any normal distribution problem, I always like to start by drawing a picture. Okay. So we're talking about a sampling distribution that has a mean of 90. So I'm going to draw a little picture. Just squeeze it, whoops, squeeze it right in here. Having some problems with my pen, excuse me. All right, let's try this again. There we go. Okay, so here is my normal distribution. Right in the middle, I'm going to put, let's see, I'm going to put some marks here and here. While I'm here, I'm going to do this. Okay, so this is my mean of 90 right in the middle. Let me see if I can move that over a little bit. And this is my value 85. It's not going exactly where I want it. All right, and then over here is my value 92. Okay, so we want everything in between those two values, just like what we did in chapter 6. All right. Notice that this is the sampling distribution, so I'm going to label it with an X bar. Okay. All right, so the central limit theorem for means says that the mean of this distribution is still 90. I've kind of already used that. However, the standard deviation of this distribution is not 15. Again. Okay, this is the only way to know how to find it. All right, there we go. The standard deviation of this distribution, instead of being 15, is 15 divided by the square root of 31. Okay. All right, other than that, it looks just like chapter 6. I wish I could, oops, I'm sorry. All right. So what I'm going to do is find z-scores for these two values in the problem. Let's get rid of this picture. I'm kind of debating whether I should draw another one. That was kind of a little bit of a pain, but you know what? I think it's worth it. All right. All right, not the greatest picture. I really need to get myself a tablet. Okay, so now I'm in the standard normal distribution. So these are z values. Okay. All right. This is the z-score that replaces the 85, which is a negative 1.86. Try to get that in there best I can. And over on the other side is going to be the z-score that replaces 92. So that z-score comes out to 0.74. Okay. Now, they didn't really show their work for what's on the bottom, so I'm going to try to explain that a little better. Thank you for hanging with me while I hope that's not completely useless. Okay. So we're looking for the area between those two z-scores. Okay. So if you remember from chapter 6, the way we did that is we went over to the table. So I'm going to exit out of this for just a second, except that I lost my mouse again. Oh, I think this time I almost had it. Oh, there it is. Okay, there we go. All right, so I'm going to exit out of this real quick. So the way that you find, oh, there's the old PowerPoint. We're not using that one. The way that you find the area between two z-scores, oh, I'm happy to have this picture still here, is you look up the first z-score, which is 0.74. So that's going to be on the positive side of the table. Here's 0.7, and over here is 0.04. So the area to the left of 0.74 is 0.7704. So the way you've seen me indicate this before is I'll kind of draw a big arrow at the top. This is all the area to the left of 0.74. And then I'm going to go over to the negative side of the table, and I'm going to look up negative 1.86. Let's see. Oops. Okay. So here is negative 1.8, and if I go over to the column with the 0.06 on top, that's this column here, 0.0314. So that is all the area to the left of, there we go, negative 1.86, 0.0314. Okay, I'm pretty sure there's another example or two after this. Probably this is the only one where I'll do this much explaining with how to use the table. Okay, so to find the area between those two z-scores, you just subtract those. 0.7704 minus 0.0314. And that is how they got okay, 0.0336. That's not the same value I got. Let me just make sure I didn't make a mistake. Negative 1.86. Nope, I think we're right and they're wrong. Looks to me like they were looking at negative 1.83. All right, so that should say 0.0314 on the PowerPoint. That's something I didn't catch. Let me see, can I edit this? Oops. Yes, I can. Uh-oh, no, I can't. Okay, I'm not going to chance it. All right. But I will type this in underneath. So the correct thing that it should say here is 0.7704 minus 0.0314. Let's see if I can do that math in my head. I believe that comes out to 0.7390. All right, so they were pretty close. Still rounds to 74%. So the probability that the sample mean is between 85 and 92 is still about 74%. All right. Next. This is just explaining how to do that on the calculator, like on a graphing calculator instead of using the table. So I'll let you look at that if you're interested. Okay. All right, so here's another example, very similar. This is one that you could pause the video and try first. An unknown distribution is created by the birth weight of males in a certain country. This distribution has a mean of 7.8 pounds and a standard deviation of 1.2 pounds. A sample with size 150 was randomly drawn from the population. What is the probability that that sample mean is less than 8 pounds? Okay, so this sampling distribution, not the original distribution, but the sampling distribution, is still going to have a mean of 7.8, but it's going to have a standard deviation of 1.2 divided by the square root of 150. Okay. All right. I'm not convinced that this is the correct thing to type into the calculator for this calculation if you're using the calculator. If you're not using a calculator, don't worry about it. All right. So the original distribution, or the sampling distribution, let's just go to the sampling distribution. It has a mean of 7.8. We're looking for the probability that the sample mean is less than 8. All right, so we're looking at this type of normal probability. Okay, so what you would do to do this using the table is you would have to change this 8 into a z-score. I'm going to try something a little different because it's really hard to write with this mouse. So the z-score, remember you have to use the new version of the formula. So upstairs you would write 8 minus 7.8, and then downstairs you have to use the new standard deviation 1.2 divided by, and sorry, I don't know how to write a square root on here, so I'm just going to do this. Okay. All right. And of course, I don't have a calculator within reach right now. Oh, you know what? Let me grab one. All right, I'm back. So while I was gone grabbing my calculator, I noticed actually that what the paragraph that had been here was completely wrong. I don't know where they got their answer. I checked my answer about 3 times. So I went ahead and just swapped out that paragraph. So the way that we would normally do these is we would calculate the z-score corresponding to that sample mean. And you can see how I did that. Now I got to find my mouse again. There we go. You can see that I am obviously not a professional at this, right? You can see how I did that here. So using the new version of the formula, here is the sample mean. There's the population mean. Dividing by the square root of the, by the standard deviation of the sampling distribution, that comes out to 2.04. So using the table, the probability that z is less than 2.04 is actually 0.9793. So the probability that the sample mean will be less than 8 pounds is nearly 98%. Way off from the answer they got. Still don't completely understand how they got that answer. All right, here's another example. An unknown distribution is created by the average number of grams of gold per million tons of seawater. This distribution, as you've heard a few times, has a mean of 1 gram and a standard deviation of 2 grams. A sample with size n equals 200 million tons was randomly drawn from the population. Using the central limit theorem for sums, what is the mean and standard deviation for the, and they did it again, sample, that should probably say sample sum distribution. What is the probability that the sample mean is greater than 1.5 grams? Okay, well, that is definitely a mean. That is not a sum if our sample is size 200. So let's see what they do with this. Okay, so I'm a little, oh, actually, the way they put this in, this does look correct. All right, again, they are using the calculator. The way that we would normally do it is we would draw our normal distribution with a mean of 1. And they want to know what's the probability that the sample mean is greater than 1.5. Okay. So I'm going to say that if you haven't tried this problem already, you should probably pause the video and try it. Okay. So we will convert this 1.5 into a z-score. All right, so I'm just going to type that in here. I'm not going to try to make it look pretty. So you would go the sample mean minus the population mean, and then divide by the standard deviation of the sampling distribution, which is 2 divided by the square root of 200. Whoops. Okay, and now that I have my calculator handy, let's see, 1.5 minus 1 divided by parentheses 2 divided by the square root of 200. Okay, that z-score. No, I don't think I believe this either. Hold on just a second. Hi there, I'm back. So yes, sure enough, they had another mistake on this slide. When I calculated the z-score for this sample mean of, sorry, I lost my mouse again. For this sample mean of 1.5, that z-score came out to 3.53. So I knew that that answer they had here couldn't be correct. And I checked it on my graphing calculator, and sure enough, I got a different answer. This looks more like the answer I would have expected. Now, if you're doing this problem with the table, let me just draw your attention to something. 3.53 is a very high z-score. So when you go over to look for that z-score on the table, what you find is something that says 3.5 and up. So 3.53 is just a little bit bigger than 3.5. So what this is saying is that the area to the left of a z-score that's 3.5 or bigger is at least 0.9999. And let's see, get back to the slide we were on. So if I was doing this problem with the table, I would say this area over here to the left of 3.53 is 0.9999, which means that the area to the right, sorry, that time my mouse actually got stuck, is 1 minus 0.9999. So if I was using the table, my answer for this probability would be 0.0001. when I used my graphing calculator, I got this answer 0.000203. Okay, so that should be a little bit more accurate. All right, and that is the end of the video on chapter 7.